Okay, so I actually am very happy to introduce to you today's colloquium speaker, who is Professor Irene Tamborra from the Niels Bohr Institute of the University of Copenhagen. After her graduation from the University of Bari in Italy in 2011, Irene received the prestigious Alexander von Humboldt Fellowship and moved to the Max Planck Institute for Physics in Munich. In 2013, she then became research associate at GRAPPA at the Center of Excellence of the University of Amsterdam. And soon after that, Irene joined the faculty of the Niels Bohr Institute as an assistant professor in 2016 and became full professor in just 5 years, which is quite an accomplishment. She is also a leader of the AstroNew group at the Niels Bohr Institute, that consists of several postdocs, PhD, and master students. During her academic career, Irene has received many awards and grants for her research, including the Willum Young Investigator Grant in 2016, the Carlsberg Distinguished Associate Professor Grant, and the Merak Prize for Best Early Career Researcher in 2019. Of course, there are many others, and if you're interested, you can take a look at her CV later. Irene's research interests lie in the field of particle and neutrino astrophysics, but she has also performed stellar work in the fields of core collapse supernovae, stellar nucleosynthesis, and cosmology. So I would like to thank you, Irene, for accepting our invitation and being here with us today, even virtually. And the floor is yours. Thank you very much.
Thank you. Hello, everyone, and thank you, Maria, and everyone for the invitation. And I am happy to be with you, and just feel free to interrupt me if you have questions during the talk. So I'm going to share my slides, and I think you see them now, right?
Yes, everything.
Okay, perfect. So I want to tell you a little bit about neutrinos as messengers of the universe. And the reason why I want to cover this is that usually we are used to learn about astrophysical environments by looking at them through photons. And indeed, here you see what was called the Grand Unified Photon Spectrum from Russell and Turner in the 90s that gathers all the information that we have about the universe through photons at different energy ranges. And however, today we have more particles that can hide us in and help us to explore the universe. And those are, of course, the cosmic rays, neutrinos, and gravitational waves. And what I want to do is first to give you a very brief overview on the current status of neutrino astronomy. And then I will focus on neutrinos in compact astrophysical sources and in cosmic accelerators. And I will give you a glimpse on the possibility of exploring also physics beyond the standard model by using astrophysical sources before to conclude my talk. So neutrinos, for those of you that are not expert with these particles, are the second most abundant particles in our universe. And they exist in 3 different species, Nu, Nu mu, and Nu tau. And they have this feature that they are very elusive because they interact very weakly. But at the same time, this is exactly the reason why we need them in astrophysics, because then we can basically gather information that otherwise goes lost through other probes that instead are interacting more often. And indeed, here you see an example of different probes. And for example, if we compare neutrinos to protons, protons are changing their trajectory very often because of magnetic fields, or for example, photons can interact very often. And so they basically lose the information that instead neutrinos are carrying intact. Another thing also to consider, as we will see in the following of this talk, is that when it comes to neutrinos and gravitational waves, they are also produced deep inside in the core of compact sources, like, for example, supernovae or mergers. And therefore, they allow us to look at the physics under extreme conditions that is ongoing in these sources that we cannot probe with other means. So if we think then of neutrinos as astrophysical probes, then we can reconstruct an energy distribution as we do for photons. Then we can reconstruct an evolution of the neutrino signal as a function of time. So instead of the light curve, then we have the neutrino curve. And then we have additional information that would be their flavor. So if you want, we can link this flavor to the polarization that we have for photons, but we have a tree. And since neutrinos can change their flavor, then this information carries also, this variable carries information about the physics of neutrinos themselves. So the idea of using neutrinos to learn about astrophysical sources has been a dream for a long time. Indeed, in the 30s, Bethe and peers were saying that there is no way we can actually observe the neutrinos unless we invoke new forces. And then John Bacall, that has been a pioneer in the field in the 60s, started to grasp the potential that these particles could have. And indeed, it was saying that only neutrinos with their extremely small cross-sections can enable us to see into the interior of a star. However, in his book at the end of the 80s, which was titled Neutrino Astrophysics, he wrote the title is more of an expression of hope than a description of the book contents. But the observational horizon of neutrino astrophysics may grow, perhaps in a time as short as 1 or 2 decades. And indeed, he was right, because then right now we are actually doing neutrino astronomy, and we can use these particles to learn about astrophysical sources. So the first example that we have that has been very successful in this respect is the sun. And here you see an image of the sun that has been taken through neutrinos. And the way this has been done is that in Japan, there is an experiment, Super Kamiokande, which is a water Cherenkov detector. And there is a reaction channel, which is the scattering of neutrinos on electrons that preserves the directionality of the incoming events. So by using these reactions, then it's possible to basically reconstruct an image of the sun like the one that you see here. But the reason why solar neutrinos have been very important is that through the detection of solar neutrinos, we have been able to test the standard solar model. And also the fact that we didn't observe the neutrinos, the number of neutrinos that we were expecting, has led to the discovery of the fact that the neutrinos can change their flavor. Then the second example of neutrino sources that we have studied really a lot are supernovae, and in particular the supernova of 1987, which exploded in the Large Magellanic Cloud. At that time, most of the neutrino detectors were off for several coincidences, and therefore we only could gather an handful of neutrino events that are the ones that you see here. However, despite the fact that, for example, today we would see, if a supernova were to go off in our galaxy, we would see 1 million of neutrino events just only with one detector. Still, with these few events, we have had the first proof of the stellar collapse, and also they have been extremely powerful in constraining a lot of, for example, non-standard physics properties, or also properties of the neutrinos themselves. And today we still observe the remnant of the 1987A in photons, and here indeed you see an image where various wavebands have been overlaid onto each other. The third example are higher energy neutrinos, and indeed in 2013, the IceCube experiment at the South Pole detected 2 neutrinos with pevatron energy, and this is the highest energy ever observed. And today we have a few hundreds neutrino events with the statistics that keeps growing. And we are sure that those events are coming from astrophysical sources, but we don't know yet from which sources they are coming from, although there started to be some likely associations of some neutrinos to sources. So what is coming next? What you see here is the grand unified neutrino spectrum that we put together recently in analogy to the grand unified photon spectrum of Russell and Turner. And here you can see that those are all the sources emitting neutrinos that we know of. So you can see that we have a very wide range in energy and about 42 orders of magnitude in amplitude of the neutrino flux. Now, the parts that are least known of this spectrum are its tails. So we have here in the low energy tail, those are the cosmological neutrinos with the cosmic neutrino background that still has to be detected. And then at the high energy neutrinos, we have the ice cube neutrinos and then the ultra energy neutrinos, which we still have to discover. And so what I'm going to do in the following of my talk is to start from the MEV region and go up. And mostly because this is a region where we really have a lot of unanswered questions to address. Of course, there are also a lot of unanswered questions concerning the cosmological neutrinos, but in the interest of time, I won't talk about it. But if you have questions, just feel free to ask. So, right now, we have a lot of detectors that are ready to detect neutrinos from of astrophysical origin. And here you see a map that summarizes all existing detectors, and the ones in parentheses are currently under planning or construction. So one thing that is interesting is that these detectors are exploiting also different technologies. And this implies that some of them, for example, are sensitive to electron antineutrinos, while others will be sensitive to electron neutrinos or others to the non-electron flavors. And so this means that at the moment we are in the position of, for example, observing neutrinos from one astrophysical source in different flavors with different detectors. And so this will all provide a complementary information, which hopefully will be very helpful in learning more about the physics of these sources. So in addition to existing detectors, or anyway, detectors in construction with the traditional technologies, we also have new kinds of detectors that are coming up online. And in the low energy frontier, we have direct detection dark matter experiments. So in this case, since we don't detect dark matter, we are going down to touch the neutrino floor, which is usually a background in dark matter searches. And this means that basically we can do astrophysics by using these kind of detectors. And so here you see this is Darwin, which will be the successor of the Xenon experiment, as well as Dark Side and Argo, that are all working experiments. And they rely on the coherent scattering of neutrinos on nuclei. So in this case, it would be Xenon, and this case would be Argon, which is flavor insensitive. So although then we will have less statistics than what we expect with dedicated neutrino detectors, the fact that it's flavor insensitive allows to offer very complementary information that, for example, is not plagued by uncertainties due to flavor mixing. And recently also we proposed the Resinova detector, which would be a dedicated neutrino detector, still based on coherent scattering of neutrinos or nuclei, but in this case based on archaeological lead, that therefore will allow to achieve a very pure signal. And the nice thing about these kind of complementary detectors is that while when we think about ice cube, we are talking about 1 kilometer cube detectors, those are really tabletop experiments. So they are really complementary to traditional technologies. On the other hand, if we go to the ultra energy range, we have a lot of radio arrays that are coming online to detect neutrinos that follow up existing experiments like Ara and Arianna. And the idea is to push towards the beyond the PEV region, which now we are starting to explore. So we have a very rich experimental landscape, and then the question is what we can learn with all these detectors. So one interesting thing concerns compact sources, and in particular core collapse supernovae. So do you know that the supernovae are coming from the death of stars that are at least 8 times heavier than our sun? And their whole explosion mechanism is basically driven by neutrinos. So we expected that 99% of the binding energy of a core collapse supernova would go into neutrinos. And therefore, we also expect a lot of neutrinos that will reach us on Earth. However, what we can see and what we can learn depends from the distance at which the supernova is exploding. So, for example, if we consider a galactic event, then we expect 2 or 3 supernovae per century. But as I mentioned already before, right now we expect to see 1 million neutrinos from one event, from one supernova, which means that we will be able to discriminate small-scale features in the signal and really learn a lot about this collapse, stellar collapse. As we go more far away in distance, then the flux of neutrinos decreases as the square of the distance, which means that we expect to see 1 burst per year, but also we will have less statistics in neutrinos. And so we started to become more sensitive to the general property of the collapse. And then as we go on cosmic scales, then we expect to see 1 supernova per second. And in this case, what we are going to detect is what is called the diffuse supernova neutrino background, which is the diffuse background of all neutrinos coming from all supernovae exploding somewhere in the universe. This is a guaranteed signal, which will tell us about the properties of the supernova population instead. And as I will mention later, we are in a very good stage at the moment to actually detect this signal very soon. So if we then go on the first extreme and we think about a local event, then in an ideal situation when the next supernova explodes, if it is very close by, then we could see pre-supernova neutrinos that are coming from the latest stages of burning of the massive star. And then we will see a neutrino signal that lasts for about 20 seconds or so, which will be emitted together with the gravitational waves. And only a few hours, up to 1 day later, we will see the shock breakout in photons and then the light curve. So one of the things that we can do by detecting the neutrinos and also gravitational waves is to probe the mechanism through which a supernova is exploding. Indeed, at the moment, this is still very uncertain, but one of the possibilities is that the shock wave starts in the iron shell, and then it's revived by neutrinos that are providing new energy to the medium, and then this triggers the explosion. And here you see some snapshots of a 3D hydrodynamical simulation. And here, this is the protoneutron star, and this blue contour is the shock wave, and those are isocontours of entropy. And what I want you to look at from this thing is that we start from something that is spherically symmetric, and then we have large-scale asymmetries and convective plumes that start developing. And those plumes are reflecting basically those bouncing, sloshing motions that are occurring in the star just before the explosion as the shock is revived. Now, what happens is that if we look at the neutrino signal, and this is, for example, the signal that would be detected in the IceCube experiment as a function of time, we would see that this signal is modulated, and it has this large amplitude sinusoidal modulations that are tracking this bouncing of the shock wave as it is acquiring energy. And we can even compute analytically, which is this frequency as of bouncing of the shock, because it depends on the evolution of the shock radius and the protoneutron star radius. And the nice thing is that we can get the same kind of information also from the neutrino signal. And we can get the exact type of information also from gravitational waves. Indeed, at the moment we are combining basically these two signatures. We are in the position of combining these two independent signatures. Now, another aspect which is also very interesting is that not all supernovae lead to the formation of a neutron star, because we have some collapses that instead lead to the formation of a black hole. So when this happens, we probably won't see any electromagnetic radiation, and neutrinos together with the probably gravitational waves will be the only probes that this collapse has been ongoing. And neutrinos are carrying a very clear signature of black hole formation, that is that the signal suddenly stops at the moment in which we have the formation of a black hole, while otherwise it will decrease exponentially as the protoneutron star starts cooling. So in this case, then another feature that is also interesting is that if we look at 3D simulations of these kind of collapses, then we have very strong modulations in the neutrino signal that are coming from these sloshy motions that are just ongoing while the star is in the instant just before what would have been a successful explosion. And if we decompose this signal in frequency, then we can see some modulation, some change in time of the frequency. That is, this is the spectrogram of the neutrino signal. And here these red regions are tackling basically the evolution of the frequency of the modulations of the neutrino signal. And so here you can see that the frequency is going down and then up and then down again. And this is basically tracking the evolution of the shock radius that is contracting and then expanding and then contracting again just before the black hole forms. So by looking at the neutrino signal and also gravitational waves, then we can really learn what is happening just a few instants before a black hole forms, which is something very interesting. Moreover, as I mentioned before, we can get basically neutrinos arriving to Earth earlier than photons do. And in this, indeed, currently we have a network of neutrino detectors that are basically like organized to detect neutrinos in coincidence with each other, so that then they can release an alert to astronomers and gravitational wave astrophysicists to point their telescopes in the right direction. And this is called SNEWS. It has been recently rebooted as SNEWS 2.0 to take into account more detectors that are currently available, as well as multi-messenger opportunities. And in principle, if you go on the web page, you can sign up and then you can get a text message as soon as a supernova explodes to then start to look at it very early on. And this is also interesting because we can do pointing with the neutrinos. So as I showed you before with the sun, we can exploit some detection channels in some of the detectors that allow to reconstruct the direction at which the core collapse is occurring. And this could also be done through triangulation if we can see one supernova going off with the 3 different detectors. This is quite interesting because, as I mentioned, there could be supernovae that are actually not going into supernovae, but collapsing into black holes. And so we don't see them electromagnetically. And right now we have evidence that at least up to 40% of all stellar collapses could lead to black hole formation. So it could be a large fraction that we miss electromagnetically. But also there could be some supernovae that are dim because of dust. And so neutrinos instead wouldn't have these problems. So if then now we go on the other extreme and we think about the diffuse signal of neutrinos coming from all supernovae exploding somewhere in the universe, this signal, as I mentioned, has not been detected yet, but this is a plot which has recently been released by the Super Kamiokande collaboration. And here you see the current upper bounds, experimental upper bounds on this signal. And here instead you see the theoretical models. So what is interesting is that already some of the most optimistic models are being excluded. And in addition, here to detect the signal, what is crucial is that we need to discriminate the signal over the noise. And since this is a steady signal, this is a challenging task. So at the moment, the Super Kamiokande experiment is being enriched with the gadolinium, which basically enhances the signal over noise ratio. And so in this way, then we hope basically to detect the DSMB within the next few years. And then this would open the floor of low energy neutrino astronomy to cosmic scales. So the reason besides that this is something interesting by itself, but the reason why it's interesting when we think about the supernova population is that for example, the normalization of this flux depends on the rate of supernova that we have in the nearby universe. And moreover, if we have black hole forming collapses, then the neutrinos have typically higher average energies, which means that the spectrum becomes steeper. So we can basically constrain the fraction of black hole forming collapses through neutrinos, which would provide information that is complementary to the one that we have with the photons. However, while we are approaching the detection threshold, we still have a lot to do theoretically, because we know that the modeling at the moment is mainly affected by astrophysical uncertainties. And especially there are uncertainties on stellar evolution. And for example, mass transfers and mergers, if supernovae happen to be in binary systems and so on, can induce some variations in this signal, which at the moment are not yet modeled in a way which is complete. But still we are making progress, and these are very exciting times. And in addition to detecting the DSMB with the Super Kamiokande, another interesting aspect is that we want to detect it with all flavors, so that again we can then put constraints on the physics and on that we have both about the supernova population. And so recently we also proposed the possibility of exploiting coherent neutrino nucleus detectors that I mentioned before, to place upper limits on the non-electron flavors, which otherwise are going to be extremely loose. And this seems actually doable. Of course, those detectors are smaller, so we don't have a lot of statistics to actually detect the DSMB. But still, at the moment, basically already with the xenon 1 ton, we can put the constraints that are comparable to the ones that we have from Super Kamiokande in the non-electron flavors. And so in the future, this will get much better, which would be very helpful to extrapolate then astrophysical information from the detection of this signal. Now, this is like about the things about the physics of the stars that we can extract through neutrinos. However, there is a problem, because these particles, as I mentioned, are changing their flavor. And when we are in stars, then they can interact with the matter background, and this leads to the well-known MSW effects, which means that the neutrinos can change their flavor in an enhanced way when they, for example, are in a background of electrons. But in the case of supernova, since the density of neutrinos is extremely large, then there is also the scattering of neutrinos onto each other, which is, again, it's a forward scattering like this one, but just on neutrinos, which can affect the flavor evolution. Now, as you can see, this basically leads the all flavor evolution to be a nonlinear phenomenon, because we needed to take care of the feedback of the neutrino field onto itself. And also, we have recently realized that then it becomes also important to consider which is the angle between the scattering, the neutrinos, the momenta of the neutrinos that are scattering with each other. So it's a bit of a complicated issue to deal with. And until very recently, when we run hydrodynamical simulations, we don't consider the fact that the neutrinos change their flavor. And indeed, neutrinos are basically treated as radiation. And this was justified because here you see a zoom in into the star. And so this is basically the protoneutron star. So neutrinos start to free stream from here. And then this is the shock radius. So all the explosion physics is happening in this part here. And then we thought that the flavor mixing was basically starting to take place only in these outer shells. So that meant that the all explosion physics was not affected. And therefore, flavor mixing would have been relevant for nucleosynthesis in the neutrino-driven outflows, and also for detection purposes, but that's it. However, a few years ago, we started gradually to realize that these neutrino-neutrino interactions that I mentioned before actually have a lot of room to take place in the innermost regions of the star, while actually neutrinos are decoupling from matter. And this leads to flavor conversions that happen very fast in time, which are possibly likely to equalize all the fluxes with each other. So if this happens, this is kind of a big deal because it means that we have to include then neutrino mixing into hydrodynamical simulations. And therefore, this has triggered really a lot of work in the past few years to try to address this question and understand whether indeed this is a problem. And so there have been a lot of attempts to rely on hydrodynamical simulations and try to see whether we do have conditions that are prone to the development of flavor mixing in this region. And indeed, we can confirm that this is the case. But since this is complicated, so we cannot solve the full quantum neutrino transport numerically, then what has been done is to rely on the linear stability analysis that basically is telling us whether there are conditions that are favorable to the development of flavor mixing, but then we don't know how much flavor mixing is taking place. And so the linear stability analysis is telling us that in this region, indeed, there are these conditions for flavor mixing to occur. And what we are trying to answer now is whether the flavor mixing is occurring in a we have a lot of flavor mixing. And so then this means that we need to worry about developing a quantum neutrino transport to include in a supernova, but also in mergers. And so we have tried then to include effects that are not included when we model flavor conversions. That is, for example, the collisions that the neutrinos could have with matter in the proximity of the protoneutron star, or the fact that the neutrinos are advected while they are changing their flavor. And all these effects that cannot be captured by the linear stability analysis, that instead is a local analysis of the conditions of the neutrinos with different flavors, have actually started to tell us that things are more complicated than they can be foreseen with the linear stability analysis. And still we have more work to do, but there is progress towards a more realistic assessment of how much flavor mixing is taking place in the innermost regions of the star. So another source which is also interesting for what concerns neutrinos are compact binary mergers. And they come from the merger of two neutron stars or a neutron star and a black hole. And in this case, those are truly multi-messenger sources. Indeed, we can see neutrinos that have MEV energies like the ones I have just been mentioning for the supernova from the disk, but then we can also produce high energy neutrinos in the short gamma ray bars. So we can produce photons, we see cosmic rays and so on. So when it comes to MEV neutrinos produced thermally, one interesting aspect is that, of course, we could in principle see these neutrinos like we would expect to see them from a supernova, but we don't have a lot of mergers nearby. So the possibility of seeing these neutrinos is negligible. However, neutrinos are still interesting, and the reason is that we think that the mergers together with the supernova to some extent might be the locations where all the elements heavier than iron are originating. So in order to enable the production of those heavy elements, we needed to enable the arc process, which requires a very neutron-rich environment, which is the case in the case of two neutron stars that are merging. However, the main reactions that are occurring in this case are beta decay reactions of this kind. So if then we change, for example, the amount of Nui or Nui bar that we have in the star, because we let them oscillate into other flavors, then we are going to change the proton over neutron ratio into the merger. So the problem of understanding how neutrinos are changing their flavor becomes relevant if we want to make predictions of the heavy elements that are synthesized in the merger. And again, at the moment, neutrino transport is not a quantum transport, also in the context of hydrodynamical simulations of compact binary mergers. However, we tried to look at this with a critical perspective and tried to simulate what would happen if we have a merger with a black hole as a compact object in the center, and we take care of the fact that the neutrinos then can change their flavor. And what we find is that we can boost the fraction of lanthanides by a factor of 1,000 with respect to the case where we don't include flavor mixing. And so this is interesting because it means that the early emission of the kilonova, instead of appearing blue, would appear red. So, of course, in the case of the 2017 event, this was not a problem because most of the neutrino-driven winds are emitted along the axis of the merger, where this is the disk and this is the axis. And so the 2017 event was slightly off axis, and this meant that we were not strongly affected by the effect of neutrinos. But as we observe more and more kilonova in the future, if we happen to see them on axis, then we really need to understand what neutrinos are doing and how they can change the fraction of heavy elements that we could expect to see at Earth. Of course, as I mentioned, then in addition to thermal neutrinos, we can also produce non-thermal neutrinos in the aftermath of the merger, and so in the short gamma ray burst, which is formed soon after the merger. And in the case of the 2017 event, we didn't see any of these neutrinos. But again, if the GRB were to explode on axis with respect to us, then there are theoretical models at the moment that suggest that we could see some high energy neutrinos coming from there. And in addition, for example, if we have a millisecond pulsar that forms at the center, then we would see very characteristic high energy neutrino signatures that could be detected also together with the gravitational waves. So it's something interesting. Now, if we go then to the other extreme of our grand unified neutrino spectrum, and we go to higher energy neutrinos, those are the ones that are produced by cosmic accelerators. And as I mentioned, we have now a few hundreds of neutrino events that have been observed by the IceCube experiment. We know that most of them are coming from beyond our galaxy. And here you see a map of current neutrino events, and we have some possible likely associations of neutrinos, for example, with AGNs or blazars, some of them with the tidal disruption events, and so on. So things are starting to become quite exciting in this field, as the number of these possible associations is increasing. And one development is that when these neutrinos were first discovered, then there was this tendency to connect the neutrinos to the gamma rays and also, of course, to cosmic rays, because we would expect that all these messengers are produced in the same regions in the sources. However, at the moment, as we get to study both the gamma ray background as well as neutrinos better, then there is a tendency that is emerging that while we can think that the bulk of the gamma ray diffuse background is coming from blazars, it doesn't seem to be the same in the case of neutrinos. And so there is now this kind of disconnection, which is becoming more evident, that is making the picture of like connecting all the messengers at higher energies a bit more complex, but it's also more interesting for this reason. And at the same time, IceCube is then releasing several alerts, and there are follow-up programs with electromagnetic surveys in both directions. And so here you see a plot of the number of real-time alerts that have been released in the past 2 or 3 years. And you can see as now they are really growing up. And so, of course, up to now, there has been no very clear, significant detection. But as I mentioned, we have a few possible detections, and also these kind of alerts have been extremely useful to constrain nearby transients and some source populations. So one of the most studied sources in these respects are blazars, and Maria here has been doing a lot of work on this, and so it's like the group is already expert on this topic. But just to give you an overview, we know, as I mentioned, that there are likely associations of neutrinos with the blazars. So we have a few of them, which could also be like a statistical coincidence, because we have statistically a lot of these sources. However, it's becoming quite complicated to try to fit the neutrino signal together with the electromagnetic radiation at different wavebands for all these events that we are seeing, and then at the same time assuming that those are sources representative of the population. And this is possibly suggesting that when we consider then the production of neutrinos as well as electromagnetic radiation, probably the gamma rays, X-rays, and neutrinos are produced in different regions along the jet. And this then pushes towards a multi-zone modeling of AGNs and of blazars. But also there are other things from the observational perspective that requires some better exploration. Like, for example, multi-wavelength and long-term analysis of the light curve that we see from these objects. And an interesting thing, as more data are becoming available, is that there seem to be some correlations of neutrinos with the radios and X-rays that possibly suggest that those are produced in similar regions, and this serves definitely further work in this direction. Now, another source for which we have a couple, source class for which we have a couple of coincidences are tidal disruption events. And in this case, basically, we have that ZTF has released, has detected one of the tidal disruption events that have been detected by ZTF in 2019, which is one of the brightest detected up to now. Has shown a neutrino which seems to be in coincidence with this source. And in this case, then we expected to see, we have observed copious emission in the UV, and then this source had the feature of being rapidly decaying in the X-rays. And there has been also emission in the radio that has been observed. And so the neutrino that has been observed was observed about 200 days after peak. And there have been a few models that have tried to explain the neutrino production in these sources. And again, also Maria has been working on this. And at the moment, it seems that there is a possibility of actually explaining the observation of this neutrino in coincidence with the tidal disruption events. And we can assume that the neutrinos could be produced in different regions in the tidal disruption. That could be in the jet, in the outflow, in the corona, and so on. However, there are uncertainties in these theoretical models, and whether there is one model that is favored over another one is something which is still under development at the moment, especially as we get also more data and a better understanding from the electromagnetic perspective of this source. And very recently also there was a paper which was instead claiming that the neutrino that has been observed was actually observed in association with a blazar that was along the same direction and nearby the source. So another second event that was classified by as a tidal disruption event by ZTF was AT 2019 FDR. And again, also in this case, we have observed a neutrino, this time later, about 400 days from a breakout. And what has been basically mentioned from the collaboration is that this could be a tidal disruption event that is occurring in a narrow line Seyfert galaxy. And we have explored it together with astronomers and one of my students, the possibility that instead is a superluminous supernova that is actually, this source is a superluminous supernova because of the long time features of the light curve that don't become stationary, but tend to bend down. And in this case, we can indeed explain that the production of these neutrinos has occurred because of proton-proton interactions occurring between the shock and the CSM. So this is also a possibility. And so as we move forward, of course, here you see kind of a summary between steady and transient sources of the local density of these sources versus their typical luminosity of neutrinos. And the reason why I'm showing this is that you can see that we have many source classes, but most of this region is going to be covered with IceCube generation 2. So as we gather more data also electromagnetically and improve on our modeling of the neutrino production in these sources, still it seems we have a good prospect for actually then probing the interesting regions of this parameter space, and then finally also discovering what are the sources of these neutrinos. Meanwhile, in parallel, we can also use the neutrinos that we have at the moment, ignoring being agnostic about their sources, but trying to put some constraints about the sources themselves. And so, for example, we can exploit the neutrino signal that we see to constrain the magnetic field of the sources. And at the moment, we can, of course, exclude some extreme scenarios. But of course, as we gather more data, then we can become more confident about also other sources which could be more common. And the same thing, for example, could be done, actually we did it a few years ago, considering also the redshift evolution of the sources. And so we can already constrain that the sources that become very abundant at high redshifts or with a certain power in the redshift distribution evolution can be excluded. Moreover, we can also use neutrinos to learn about the properties of the sources themselves. And this will become especially interesting in the future as more detectors will become available. And for example, recently with another one of my students, we tried to investigate whether we can use neutrinos to explain this feature, which is sometimes observed in gamma ray bursts, that where there is a rebrightening in the optical and also in X-rays at late times, and those are usually called the jumps. And there is a jump indeed in the light curve, in the electromagnetic light curve, that translates in the jump, in a jump in the neutrino signal that we expected to see. And so the conclusion was that indeed, since we expect an enhancement of the neutrino flux because of this rebrightening effect in the afterglow of gamma ray bursts, then with the upcoming detectors like IceCube Generation 2, radio, and others, we could probe some of these scenarios. And so we could probe, for example, if we are under optimistic conditions and we see a rebrightening, then we would see more neutrinos coming our way, which could tell us about the mechanism which is powering this rebrightening. Because, for example, in this case, we assumed that this was given by the collision of two relativistic shells. So just in the last minute before to conclude, I also wanted to highlight that, of course, we can do a lot of astrophysics by using these sources, but those are also laboratories to do particle physics, and we get it basically for free. And here you see just a summary across the energy ranges that we have covered of the different non-standard scenarios that could be probed. And one thing which I want to highlight in this context is that we should be careful when we try to use astrophysical sources to place constraints on non-standard physics to do this work properly. Indeed, in work with one of my students, we tried to revisit the supernova bounds that are usually placed from on a KV mass sterile neutrinos that are well-known dark matter candidates. And so this is the mass and the mixing, and here we have these regions that are usually excluded by supernova. However, all these limits, and there are many other examples in the literature on other kinds of non-standard scenarios, do not take into account the fact that if we add this extra physics, then the source evolution is actually affected by itself. And so if we take this into account consistently, and we did it just by considering one slide, so without coupling this to entropy, temperature evolution, and so on, but in a kind of a bit simplified, not fully self-consistent simulation, still what we found is that basically the excluded region disappears. So supernova then basically leave the all parameter space unconstrained, and this will become even more conservative if we actually run a full hydro simulation that takes into account these non-standard ingredients. So as we move forward towards having more data and trying to learn more also about new physics, we should really be careful about the impact that these extra ingredients have on the evolution of the source itself. So this brings me then to my conclusions. We have a lot of messengers at the moment to learn about the universe, and we are just starting to model in a more sophisticated way the behavior of neutrinos in the sources themselves, but we know that they are key particles in compact sources. And they are revealing us key information about the physics of the sources, but at the same time, we can also use them as a gateway to new physics. And all this is happening while we have many detectors that are already active or they are coming up online that will provide us precious information about the universe. So that's it. Thank you.
Thank you, Irene, very much for this very exciting talk. It was very interesting for me as well, for learning about the low energy neutrinos. So I think now we have time for questions, and I would encourage everybody just to raise their hands or even unmute themselves and ask the question directly. Let's give some time because people are usually shy.
I think we have a question.
Yes, there is one question by Professor Mastichiadis.
Yeah, thank you, Irene, for your talk. You covered quite a lot of ground, and I have. I'm a little bit overwhelmed by the amount of information, but one thing about the neutrino mixing that you were talking about in the supernova and the non-linear stuff, how far you are from for having a fully developed code that you could follow the evolution of the neutrino mixing inside the proto-neutron star?
Yeah, so with the we are actually developing it, and with my group we currently have quite advanced code, but the problem is that for example we can include the collisions and we can include advection, but the problem is that this is a nonlinear problem. So as we have gone from 1D model in time in a radius to 2D, so like this one that is a 2D, then being a nonlinear problem, the instabilities develop differently. And if we go to 3D, we expect also that they will grow in a different way. So this is something that at the moment we are trying to like model better and to understand better, because it seems that by going to 3D, this could create like some extra complications. And the other thing is that when it comes to collisions, we didn't, so this is in the decoupling region of the neutrinos. And for example, like we think that the probability would be suppressed if collisions exist, like they have a damping effect. But instead, since it's a nonlinear phenomenon, what we found is that actually this is enhanced. And this requires, however, a modeling of the collision term, which still is not available like in the literature. I mean, it's available in theoretical terms, but no one has yet simulated the full self-consistent collision plus flavor evolution. So in this case, for example, with my group, we simulated it by considering some simplified version of the collision terms. So this also needs to go in detail. The other thing that also I think is important is that here, so it's not only the energy distribution of the neutrinos, but it's also the angular distribution of neutrinos that is relevant to this kind of interaction. And so as we move, because neutrinos are decoupling, the angular distributions are becoming more and more forward peaked. And this is affecting the way the oscillations are taking place, and is affected by collisions. And so there is this kind of interplay between these phenomena, which we are working to put together in a consistent fashion, but still there is quite some work to do. And mostly, as I say this, because numerically it's a very hard problem to model.
Okay,
so this
thank you.
Is where we stand.
And another question, if I may. I didn't see whether you meant, I mean, I haven't seen you mentioning the GRBs.
Yes.
You talked about AGNs, but you didn't mention GRBs, except from the afterglow at the end. What is your opinion about connection?
I didn't mention them simply because I wanted to just talk about something which was probably more complementary with respect to your local activities. So I tried, this is why I went around. But I personally find them extremely interesting sources. And so we are actually working by to modeling them. So for what concerns, if you ask about my opinion concerning the sources of high energy neutrinos, it seems that like the high luminosity GRBs really cannot explain the flux that we observe. However, the low luminosity ones, and especially choked GRBs, seems to be very interesting. And indeed, I think this is, of course, there is a bit more room, because if we talk about the choked sources, then we have more theoretical freedom, like in terms of how we can do the modeling, but they seem to be very abundant producers of neutrinos. So this is something interesting when we think about sources. And also another thing that I find also very interesting is that as is the case for AGNs, it seems also for GRBs, when we think about the production of neutrinos and so on, we really needed to consider like multi-zone models that take into account the evolution of the jet properly. So also in this case, there is quite some work to do. But like the overall picture, this of course will make everything more self-consistent with respect also to electromagnetic observations. But I think at least for high luminosity GRBs, it's difficult that it's going to affect the bulk of the neutrino flux that we expected to see from the sources. It will shift it in energy, we shift the shape, but I think not the normalization. If we think about like the main sources that are making the flux of the ice cube neutrinos that we see.
Okay, thank you. And the one comment about the AGN, and also you mentioned it for GRBs. If you introduce a multi-zone model, then of course you have so many more free parameters that you can fit everything.
Exactly.
So I don't think that, yeah. Okay, thank you very much once again.
You're welcome. I fully agree. The only problem is that it seems it's difficult at the moment, at least from work that like has been done also from Maria, to basically match all the multi-wavelength data with the neutrinos for the different sources that have been observed in coincidence, and then have a clear picture that actually is also representative of the population. So either there is something that we don't understand in terms of production of these particles, or probably they are produced in different regions of the jet. But I agree that as we go to multi-zone models, then it becomes easier to fit everything because we have more parameters. I fully agree.
Okay, thank you.
Okay, so are there any other questions? I have also a couple, but I can wait to see if there are any other. I see one from George. Yes, go ahead and I will ask later.
Yeah, thanks very much for the very interesting talk. I hope I have some bells here. I hope they are not too loud.
I can hear you.
You can't hear me?
Wait.
Oh, okay. Sorry, there is a church light just outside the office. So I'm trying to formulate the question, but like you mentioned that all these simulations that you have, like they don't simulate yet the full collisional times. Like there are very complicated simulations, and I'm curious, like in the future, these plans. I mean, we are at the point that where we have supercomputers and like more and more detailed simulations are coming ahead. But you also mentioned like the comparison of giving some smoking gun, let's say, for observation. So, like in the next 5 or so years, what would be something that would change the consensus? Like, what would be something that is really important for that? Like getting better data. I mean, for GRBs, we have all this data, multi-wavelength, the last 10 or more years with Swift and multi-wavelength follow-up. AGNs the same. And so I'm curious, like, what's going to be the improvement in the next 5 years, or like in terms of simulations or future missions or observations that could help you like solve this mystery?
Yeah, so I think it's different from low energies and high energies. So in the low energy regime,
yeah, you have lots of neutrinos.
For so there, like for what concerns supernovae, of course, we are in view of we need a galactic supernova now. It's more than 30 years, so we actually statistically are really waiting for it. But also, like they could come from beyond our galaxy. And now we have all these surveys that are ongoing, like in real time, which are discovering all sorts of very weird supernovae, which are revealing a lot about these classes of sources. So this is really like a kind of opening up a diversity into the population, which up to now we kind of didn't really knew about. So this is happening observationally. From the modeling side, right now, basically hydrodynamical simulations have reached the 3D frontier. But while it's easy to make explode low mass models, high mass models are difficult to explode. And it has been shown that there are ingredients, and one of these could be a mixing of neutrinos that are missing, or like uncertainties on cross sections, for example. And they can do the job. So if we add them, they actually explode because they are kind of in an unstable situation. So the smoking gun would be to actually reach a level where we have consensus and like a stable explodability for classes of models at different masses. And at the moment, like we had the first like 3D simulations maybe like 6 or 7 years ago. So right now we have a broader sample, but still we are missing agreements. Like we don't have all of them exploding, and different groups. I mean, we are in agreement with the overall features, but these things are like these little ingredients that are missing seem to be crucial, and as we progress, it seems to become more and more important. So the smoking gun would be then on the theory side, much observations, but have then things also matching among the simulations from different groups with the successful explosions. And for mergers, it's even worse because they have been traditionally not so studied as a supernova. Plus, there is the complication of the geometry that is like a disk and not a sphere. And so there is a lot of work to do. And specifically for neutrinos, neutrino transport is not advanced at all. So there is a lot of work to do also, especially because we are going to see many more kilonova in the future. And therefore, we needed to match observations, and we needed to understand what is going on. In the high energy frontier, I think it's basically now going towards real-time astronomy, also with the neutrinos. And so these data are going just to come, but we really needed to get busy on the theory side, because there, up to now, simplistic models were like, okay, because we didn't see data, but as we go towards receiving more and more data, it becomes necessary to have models that are more sophisticated. And this is, as we were discussing before, maybe going to multi-zone, maybe staying one zone, but developing something that is better tailored towards understanding the data and so on. So yes, I think within, like in the near future, these are like the most interesting thing, or most urgent things to be addressed.
Thank you. I think that covers my question.
Okay, so there is still time for questions. Yeah, I see Annika has raised her hand. So.
Yeah, maybe a bit of following up on the multi-zone models. I'm always wondering, like, obviously there is on one hand a need to invoke these and in order to explain observations, but then again you have a lot of free parameters, as Apostolos mentioned, and it's very true. But I was wondering, are there any other observational constraints that could limit the number of free parameters, or maybe hydro simulations, other things to consider that would allow to have a multi-zone model, but give information on the free parameters that one introduces? Does the question?
I mean, I think that if there are different ways of like having, for example, multi-zone models. So if you then just put in various parameters and then you just have the freedom to match them to fit the data is one thing. But for example, if this is done consistently, for example, also together with hydro simulations of jets and so on, probably this helps because at least you have like, you are guided by the physics and then you can add on top of it the production of particles and so on. So I mean, it's definitely more complex because anyway, the number of degrees of freedom increases, but yes, also we have more electromagnetic data now that are becoming available in different wavebands. So all these things could be combined and probably reduce these uncertainties. But there is work to do also in this direction.
Yeah, thanks.
Is there any other question from the audience?
Hello.
Marcos?
I have a quick one. Is general relativity concerned in this type of flavor mixing simulations?
Yes, that's a good question. Yeah, it is interesting. It's especially because, as I mentioned, it's interesting. It matters like the angle with which the neutrinos are scattering, and so the trajectory with which they are propagating can be bended by in the proximity of the compact objects. However, given the level of complications that we are dealing with at the moment, this effect is not really considered. So this would be the next level of the next term in the equations to be added. But it is included in the hydro simulations. So if we do like post-processing to understand how neutrinos are changing their flavor, then somehow this is taken into account, but it should be done better.
Okay, perfect. Thank you.
You're welcome.
So I don't see any other hand raised, so maybe I can ask my question now. So I was wondering, Irene, you mentioned about this, the time signature of the SASI, of the instability on the neutrino curve. And I was wondering if you have any, yes, two questions. First of all, if there is like a correlation between the frequencies or the characteristic frequency that you see in the neutrino curve and the gravitational wave curve in this case. And the second is what happens or in the case where you don't have a SASI-driven core collapse, but like some people suggest that you might have a fast rotating magnetized core that collapses, and then you might have a jet-driven collapse of a star. So do you expect, I suspect that you will not see the similar signal in the neutrino curve, but what would be the expected neutrino signal? Has this been computed?
Yeah, so the frequency of neutrinos and gravitational waves are connected, and they are one half of the other one. Actually, the gravitational one is half, so they are connected. And this is what I was saying, like if we see it in time, then we can see these modulations in the two. We can compute for the two of them the frequencies, and like we have from the grounds of theory, we know exactly what they should be. So like we can basically go back and do the physics of the source. So there is a one-to-one link which we can do. It's true that like these cases that I was showing are for neutrino-driven explosions. If we have jet-powered explosions, then the neutrinos, okay, before we go to jet-powered explosion, you were asking what happens if there is no SASI. Mm-hmm. And this is indeed something that depends on the progenitor. So I don't have plots in the talk, but I can show you other plots. But for example, for this model here, we had like 2 times where there was a SASI, and in between where there are those kind of small modulations, this is convection. Mm. And so what we find is that for low mass progenitors, for example, 11 solar masses models, we have only convection. As the mass increases, SASI takes over. And why this is happening is something that we are studying. We don't know. If there is rotation, then there is an interplay between rotation and SASE, which is also something which we are trying to understand better at the moment. But like I can give you some empirical features, but we don't know. But somehow then it seems that like in all higher mass progenitors, this is an effect that is always taking place in some form or the other. And as I said, it manifests itself randomly. So it goes on, sometimes it develops on a plane, sometimes it becomes sloshing and it can change the plane also while it's going. So, and through the neutrinos, we can see all these things. So for example, like here, this little thing that you see here, this is that the SASE plane is going to 90 degrees. So we see it from the simulations, and I can see because like I'm trained with by looking at all these signatures, but these things are happening. And in principle, we have, if we combine the light curve of the neutrinos, the one of the gravitational waves and so on, we can reconstruct these things through careful analysis. However, yes, those are neutrino-driven explosions, and in the case in which there is a jet that is powering the explosion, then the neutrinos won't carry most likely these kind of signatures. So there, at the moment, there are no hydrodynamical simulations that have sophisticated transport of neutrinos plus MHD. And in order to tackle like your question, how the neutrino signal would look like, we need both of them, because like most of these things, and for example, also the laser instability, which I didn't mention, but is a dipolar asymmetry between the electron-neutrino and antineutrino signal, which we observe on a larger scales. Those are all resulting from sophisticated modeling of neutrino transport. So with the more simplistic transport of neutrinos, we didn't have so prominent features. And so once we combine them with MHD, we needed to see what features will come. But there is evidence that the ones that are mostly driven through from rapidly rotating cores are a small fraction of the whole population. And so, for example, we have studied rotating models up to constraints coming from rotation of stars through the neutrino-driven mechanism. And we have seen like the features that we can see from there. But plus MHD, it's work that needs to be done. So yes, I don't know if there will be still those kind of hydrodynamical instabilities developing. But one thing which is for sure happening is that there is a directional dependence, very strong directional dependence of the signal along the jet. Which this has already been pointed out in some simulations, which however I don't believe fully because it didn't have full transport, but still it's quite reasonable.
Yes, as an expert on that. Okay, I had also some other questions, but I can leave it for now. Just to mention, going back to the comment about multi-zone models and the role of coupling hydrodynamics in order to, with radiative transfer, which is, I think, the next step. In my opinion, the less clear thing in that direction is how one can couple the microphysics with the fluid dynamics that the hydro or MHD simulations probe. Because even if you identify regions in a jet or accretion disk, where you expect to see some dissipation of energy, the question is how you're going to transfer it to the particles to do the radiative transfer calculations. And there is some uncertainty there as well. So that's my comment on that.
Yeah, I agree. And in this sense also, I think peak simulations are kind of also interesting because they kind of provide, I mean, yes, they are local, but still they provide a bridge between those two separate worlds, which in essence could be helpful to some extent to get some intuition. But I agree that it's a complicated problem to merge the two things together. Yeah.
Okay. So thank you, Irene, very much.
Thanks to you.
And I mean, since we are now 20 people still left here in the room, I would like just to request one more time to switch on your cameras, take a photo, because last time we were like we left, there was a smaller number of people.
And now that you ask that, everyone is leaving.
Everyone, okay. Because we would like to have like a photo for our website, but we still don't have one. Okay. Okay, people are still leaving, but I will try. Thank you very much for opening your cameras. Just let me take a screenshot. Here we are. Okay, that's it. Thank you very much. What happened?